Hello everyone, and welcome again to another episode of On Track Whiteboard series. My name is David Marakshi, a Senior Technical Marketing Engineer with Altium, and today I would like to go over a cool technology, printed electronics, and some of its application and design challenges. The core driver of this market has been conductive inks. Which really has been adapting to the different market trends. It somehow remained relevant by managing to find or create new uses through the all-inclusive term of printed electronics. That's why the term printed electronics has been loosely used to cover very thin devices and circuits. This is because many of these technologies and their applications overlap with many steps in common. So, printed electronics is technically referred to the method enabling the printing and a variety of substrates in order to create electronic devices, which makes printed electronics rather a process and therefore is subject to the selected printing methods that manages the process of depositing material ink on a substrate to create, for example, active or passive devices such as capacitors, thin film transistors, etc. It's meant to be a low cost in terms of processing, with potential for automation using existing technologies such as inkjet, screen printing, gravure, and other similar technologies. It's also meant to be used on a low-cost substrate such as plastics, papers, fabric, etc. Printed electronics is definitely a fast-growing technology and proven to be invaluable across all industries, including healthcare, automotive, consumer electronics, and aerospace. Really tremendous progress has been made in the printed electronics technology, as designers now have options with clear advantages to develop certain applications. Some ECAD tools also now have the option to develop a layer stack specifically for printed electronics, which comes with its own set of challenges. Since PE have become secure, flexible, and cost-effective, they have become appealing to many industries, with the potential to reduce costs, technical constraints typically associated with mass-producing electronics, and we can sum their benefits as follow. It's meant to be definitely a low cost because they use less material and less energy to work with. They offer flexible form factor. They're easy to produce. As we mentioned earlier, you can use existing technologies such as inkjet, and they're easy to integrate as well. And they definitely open a new front on non-conventional functional electronic devices such as flexible displays, active clothing, smart labels, and much, much more. So given the market potential of PEs, many suppliers are trying to ensure that first mover advantage by offering a wide array of products, which actually have led to a very diverse PE industry, if you will. Some of the applications, just to mention a few, in-mold electronics, IME, which we'll cover in a little bit more in depth, wearables, given the printing ability in fabrics, smart packaging, flexible heaters, which are now used, for example, in car seats, touch panels, photovoltaics for solar, for example, transparent conductive films, stretchable conductive inks, LED lighting, biomedical sensors, and of course, PCB printing, which can dramatically speed up the prototype phase, and many others. So I wanted to focus a bit more on the in-mold electronics. Because it seems to be one of the most promising application areas. IMEs integrate flexible circuits and electronic components into a three-dimensional molded plastics. This allows designers to print circuit directly into a plastic substrate, and that enables them to integrate touch control, lighting, and antennas in applications such as refrigerators, washers, and automotive consoles. The clear advantage of IMEs is that it eliminates the need of bulky, heavy, complex multi-layers assemblies and can be as thin as 2 millimeters. IME has been making a lot of progress with new system of conductive and dielectric inks that are designed to survive the intense stretching and heat of thermoforming and injection molding process. The market has definitely shifted from prototypes to proven volume production and reliability. IME offers the construction of ergonomically friendly control surfaces with embedded 3D circuits that can include LED lighting and capacitive switches. It makes them perfect for touch panel control applications, as the one, for example, in an automobile. And that's due to their lighter material and faster assembly process, which in turn lower the overall cost production. We can sum the overall benefits as follow. It's definitely 70% lighter, some of the study shows, because you don't have those bulky assemblies. And they are 30% cheaper to produce because you can use wide available technologies such as an inkjet. Their part assembly takes less time because you don't have those multi-layer parts that you need to assemble. So some studies show that they can be reduced by 40% in terms of timing. And it offers freedom of design. Imagine the things that designers can do. Literally, their imagination is the limit. So how are they processed? Well, functional and graphical printing are often carried out on a 2D flat substrate, which is then formed and molded into a 3D shape. If I take, for example, this mouse here, imagine this is my 3D shape, and I'm designing my circuits in a typical 2D ECAD editor. And after I'm done with my design, it gets printed on a plastic substrate, which then gets molded into the 3D shape. With all the touch control, if I have a scroll, for example, or whatever, it will be just on the top, very light, very easy to do. But some of the challenges with this is the need to survive the thermoforming. And accounting, for example, angles and odd shapes, the traces will be molded into. For this example, it's a very simple shape, but imagine something that is very curvy with odd angles. Since there's a stretching effect, if you will, to the traces when they move from a 2D to a 3D mold. So while printed electronics provide clear advantages for many applications, they still face new challenges as many companies actually are going through some trial and error to experiment with the new methods. And for PCB designers, the challenge, of course, is from a PCB tool, as there are unique requirements for the PE layer stack, special design rules, and MCAD integration. So, given the processes are new, there are challenges related to the tools used to make the printed electronic circuits. In terms of tools, how do you integrate an MCAD to ECAD as you move from a 2D design to a 3D process? How do you ensure that your product will survive to the end the thermoforming simulation? And the same thing, if you need to be able to do thermoplastic strain simulation to ensure that the 2D circuits will fit the 3D mold. And in regards to ECAD tools, well, some of the obvious ones, design rules. As I have in this example here, this is a typical PCB layout. You have the top layer and you have the bottom layer. So this is not a problem for a typical PCB because the layers are isolated. This is not a short or anything. But for an IME, these points here are actually shorts because it's a layerless design concept, if you will. And you need to have a tool that understands the rules that this is actually a short. And on top of that, the layer order is swapped. The top layer becomes actually layer 2 because it's the one that becomes on the bottom. And the bottom layer becomes the one on the top. So crossover like these needs to be resolved, and that's going to be part of the tool that needs to add a dielectric crossover, for example. So the ability, for example, to also route in 3D, if possible, because you can have a 3-mold design, you can either bring in a step file or however you do that with your current tool and be able to route the 3D on that 3D mold or whatever the 3D design that you have. How to set up global dielectric stack, because like I mentioned, it's a layerless stack and it needs to be treated differently than a typical PCB. And of course, the challenge of having access to the wide material library selection. The different vendors offer many different materials that meet different wide design requirements. For example, there's some that are good with adhesiveness, some that are better with conductivity, different type of dielectric. There's some application that needs for the ink to be stretched. So that's another issue that can face in terms of PCB design, selecting the right material from a wide library that might be available or not. So that's a wrap for us. And again, if you found this episode helpful, like it, share it, subscribe to our channel so you never miss out on future episodes. And we'd love to hear your comments. And thank you for watching.